Hi, this is a video on solving compound inequalities. Let's look at problem number 1. We have 11 is less than 3y plus 2 and less than 20. So what you need to remember is that when you see a compound inequality written this way, this is listed as really an and compound inequality because it can be both. It can be this one and it can be the other one. So in an and situation, you can write both of the inequalities separately. Once you realize that this inequality is an and compound inequality, then you solve each of the two inequalities separately. So you just go through the same way, subtract 2 from both sides, and you come up with 9 is less than 3y. Divide by 3 on both sides, so 3 is less than y. Remember, you could write this the other way. Y, notice how it's opening towards the y, is greater than 3. I'm going to actually write that out in words. 3 is less than y is the same as y is greater than 3. They're the same statement, just rewritten in opposite directions. Solve this one the same way. Start by subtracting 2. So 3y is less than 18. Divide by 3 again. So y is less than 6. Again, I like having the y on the left-hand side. This would be y is less than 6. So as you read it, the next thing that we do when we solve in compound inequalities, any type of inequality, is we graph it. So here's your number line. Notice that we're going to have to do something with the 3 and the 6. So I'm going to start here with 3. Below 3 would be a 2, then 4, 5. I finally got to 6, and I would go 1 above the 6 with 7. Since this is a greater than 3, doesn't say equal to, I have an open circle. And I'm actually going to choose to use a different color for this one. I'm going to choose to use, how about purple? So for this one, I'm going to use this purple. So it is greater than 3, and I'm going to shade in what that means. So that means it would go this direction. For the other graph, I'll use green. This one says it's less than 6. So again, this would be an open circle, and it would go less than 6. Now with an and statement means that you're only looking for where do the graphs intersect. So when you look at this, where do the two graphs overlap? Well, they overlap in the middle. So I'm going to use this color. They overlap just right here. That's where the purple and the green overlap. So my solution graph, which I'm just going to make a little bit neater, would look like this. I would have my 2, my 3, my 4, my 5, 6, 7. Y is greater than 3 and it's less than 6. Greater than 3 and y is less than 6. So it's just this part in the middle. Remember, if you can split an and statement apart when solving, you can put it back together when writing your final solution. So notice that we said y is greater than 3. That can also be written as 3 is less than y is less than 6. This is putting those two statements back together, making it into one complete graph. Now we're going to go through a second example. This is an or example. An or is saying you could have one or the other or both. So it's one or the other or both. So you again solve each one separately. It's never going to be combined together into one line inequality. So you first subtract your 3 just like you would when you're solving a linear equation. So it's less than 12. Then you divide by 6. So x is less than 2. X is less than 2. Or, so you do the other side, add 2, add 2. So 4x is greater than 20. Divide by 4. x is greater than 5. X is greater than 5. Again, it's an or statement. So x is less than 2 or x is greater than 5. So I go and I make my number line. I'm going to start with a 2, 1, 3, 4, 5. 1 above 5 is 6. I'm going to use just different colors, so I'll use like this red color for this side. So here, again, it's less than 2. So here, and then I go less than 2. If I graph the other side, it is greater than 5. I would go this way. So when I have my final solution or graph of this, I'm just going to do it all in the same color, my final solution says exactly what it has. X could be less than 2, so it could be this part, or my answers would be greater than 5. It does not have to be the overlapping part for an or statement. It's either or, and that means it could also be both. Okay, so those are 2 examples. I'm going to do one more example. So my third example is an and problem. And again means that we're looking for the intersection. Section. So we're going to solve each of these. This side you just divide by 15 on both sides. So x is greater than 2. And divide by 18 on this side. X is less than negative 2. Okay, so if I go to my graph, again I have a negative 2, so I'm going to plot something below it. Below it. Then I would go above it all the way up to 2, and then something above 2. So I have my graph. If I graph this one, x is greater than 2. It's an open circle, greater than 2. If I graph this one, x is less than negative 2. Now, this is an and statement, and we said that and statements have to be intersections. So when I look at this, does the the pink intersect the green at all? No, there is no intersection. Because there is no intersection, there's nothing they have in common. It can't be in both places at once. That means that this graph is not your final graph. There's actually no solution graph that will show you any intersections. So since there's no intersection, there is no solutions when dealing with an and problem. I'm going to do one more, even though I said I was going to stop after this one. I'm going to do one more problem. So here's my last problem. I'm going to solve for x. So divide by 4 on both sides. So x is less than or equal to 3. So it helps to write that out. Or divide by negative 7 on both sides. When you divide by a negative number, we discussed in class that you flip the inequality. So make sure that you flip the inequality when you multiply or divide by a negative number. And again, this is x is greater than negative 3. Okay, so if I go to my number line, again, starting at negative 3, put something on here that's below it, above it, keep going all the way up to 3, and then go 1 above it. If I graph x is less than or equal to 3, the equal to means that you fill it in, and my pink line will go all the way this way and keep going. That's why we shade in the arrow. If I graph the other one, x is greater than negative 3, greater than or equal to, I didn't write that down, greater than or equal to negative 3. So that means it's filled in, and I'm going to graph this way. Since we're dealing with an or statement and I said it could be in either place, either the pink graph or the green graph, what you should notice is the pink graph keeps going forever to the left, and the green graph goes forever to the right. So what that means is, since it could be either pink going on forever this way or green going on forever that way, your solution is the entire line. Because it could be either pink or green, and since either pink or green makes up the entire line, that means that all the real numbers, everything in between, all real numbers are your solution. So all real numbers are the solution. So those were 4 examples on inequalities, compound inequalities. If you have any questions, please don't hesitate to come in and ask.